For centuries, humanity has looked up at the stars and wondered if we are truly alone in the universe. Ancient civilizations recorded mysterious lights in the night sky, philosophers debated the nature of celestial bodies, and scientists have, for decades, speculated about the possibility of life beyond Earth. Now, a new chapter in this cosmic story has begun. The age-old question may finally have an answer. Thanks to a monumental revelation from NASA, we now stand at the edge of one of the most profound discoveries in history, the confirmation of life beyond our solar system. Recently, NASA's director announced something extraordinary. The James Webb Space Telescope, our most advanced window into the universe, has detected clear signs of biological activity on a distant world. That world is Proxima b, an exoplanet orbiting the star Proxima Centauri just over 4 light-years away. This finding isn't just a scientific milestone. It could redefine our understanding of life, reshape our philosophies, and ignite a new era of space exploration. Proxima b, long considered one of the most promising candidates for habitability, has now revealed something stunning. In its thin twilight region, the so-called terminator zone, a narrow band between its scorched day side and frozen night side, there appear to be atmospheric markers that scientists cannot explain by geological or non-biological means. These signs suggest the presence of a stable, enduring biosphere, possibly teeming with microbial life or something more advanced. But how did we arrive at such an astonishing conclusion? To understand that, we need to explore the technology that made this possible, the James Webb Space Telescope, or JWST. Launched in December 2021, JWST is humanity's most powerful space observatory. A marvel of engineering and collaboration, this space-based telescope was designed to replace the aging Hubble telescope and surpass it in nearly every capacity. Unlike Hubble, which observes primarily in visible and ultraviolet light, Webb sees the universe in infrared wavelengths. This allows it to peer through cosmic dust clouds, observe the early universe, and most crucially, study the atmospheres of distant exoplanets. It orbits around the second Lagrange point, L2, nearly 1.5 million kilometers from Earth, where it maintains a stable position to continuously gaze into deep space, uninterrupted by Earth's shadow or reflected light. At the heart of JWST is its 6.5-meter-wide segmented primary mirror, made from beryllium and coated with gold to reflect infrared light efficiently. This mirror is over twice the size of Hubble's and can collect far more light, enabling the detection of even the faintest signals from distant stars and planets. With this extraordinary sensitivity, the telescope captures light that has traveled across billions of years, essentially letting us look back in time. JWST's suite of instruments includes the Near-Infrared Camera, NIR-CAM, Near-Infrared Spectrograph, NIR-SPEC, Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor, FGS. Together, they provide an unprecedented view of the cosmos. NIR-CAM enables sharp imaging and stellar population studies. NIR-SPEC can analyze light spectra from exoplanets, breaking it down into its constituent wavelengths to identify chemical compositions. MIRI, operating in the mid-infrared, can detect heat signatures from cool objects like exoplanets and dusty protoplanetary disks. So, how exactly did JWST identify the possibility of life on Proxima b? The key lies in a technique called transmission spectroscopy. When Proxima b passes in front of its host star from our viewpoint, starlight filters through the planet's atmosphere. This light interacts with molecules in the atmosphere, leaving behind a unique spectral fingerprint. By analyzing these fingerprints, scientists can determine the presence of specific gases. What Webb discovered was astonishing. The planet's atmosphere shows strong signatures of oxygen, methane, and water vapor existing simultaneously, a chemical combination that, on Earth, is closely tied to biological processes. This so-called biosignature is difficult to explain through abiotic, or non-living, processes. Even more intriguing were trace amounts of chlorofluorocarbons, CFCs, compounds which, on Earth, are synthetic and typically produced by industrial civilizations. This combination of gases points to the possibility of life, possibly microbial, but maybe even intelligent. The presence of CFC-like compounds suggests energy use, environmental modulation, or technology. Scientists are cautious, of course, and emphasize that further observations are necessary to rule out alternative explanations, but the evidence is compelling enough to consider the unthinkable. We may have found life. The discovery has sent shockwaves through the scientific community. Not just because of what was found, but because of what it could mean. If life can exist on Proxima b, a world so different from Earth, with intense stellar radiation and potential tidal locking, it could mean that life is not rare. It may be a common feature of the universe, appearing wherever the conditions are right. What makes Proxima b particularly interesting is its position in the habitable zone of its star. This is the region where temperatures might allow for liquid water to exist. But Proxima Centauri is a red dwarf, a type of star known for frequent solar flares and intense radiation. For life to endure in such an environment, it would need protective adaptations or perhaps live beneath the surface or within thick atmospheric layers. Despite these challenges, Webb's data reveals atmospheric stability, pointing to the planet's ability to retain gases and sustain long-term conditions. The infrared data even suggests seasonal changes, something unheard of in our prior studies of exoplanets. This implies not just a living planet, but a dynamic one. Now, researchers are racing to study Proxima b further. Missions are being proposed that could, in a few decades, send small, light-propelled probes to the Alpha Centauri system. Initiatives like Breakthrough Starshot, backed by private funding, are exploring ways to send gram-scale spacecraft traveling at 20% the speed of light. If realized, these probes could reach Proxima b in just over 20 years and send back high-resolution data and imagery. The implications of confirming life beyond Earth are enormous. Philosophically, it would reshape our place in the cosmos. Religiously and culturally, it would challenge narratives about creation, uniqueness, and destiny. Scientifically, it would open new fields of astrobiology, exoecology, and interstellar communication. Technologically, it would fuel a new space race to explore and understand distant worlds. We would also have to ask, what kind of life is it? Is it microbial and simple, or complex and intelligent? Could it be aware of us? And if intelligent life exists there or elsewhere, should we attempt contact, or remain silent? These questions are no longer confined to science fiction. They are becoming real, urgent, and necessary. Some experts caution restraint. It's essential to avoid jumping to conclusions. After all, the discovery of potential biosignatures is not the same as direct evidence of life. We must continue collecting data, refining our models, and comparing observations. But even this early step is historic. It confirms that our tools are capable of detecting life. That Earth is not an isolated miracle, but perhaps one of many life-bearing worlds. And so, as we stand on the cusp of this new age, we are reminded of Carl Sagan's words. Somewhere, something incredible is waiting to be known. With the James Webb Space Telescope, we are not just waiting, we are discovering. From the terminator zone of Proxima b to the farthest edges of the universe, we are beginning to see that life may not be the exception, it may be the rule. Stay with us at Discovery at 2.0 as we continue to unravel the universe's most mysterious secrets. The journey has just begun.